Something is wrong with the Pacific Ocean. Not wrong in the way that climate scientists mean when they document trends and project trajectories. Wrong in the way that experienced oceanographers mean when they look at a data set and go quiet for a moment before speaking. The Pacific is the largest single feature on the surface of this planet, covering more area than all the land on Earth combined, and its behavior shapes the weather, the fisheries, the monsoons, the drought cycles of half the populated world. When the Pacific does something unexpected, the consequences spread outward through atmospheric circulation patterns and ocean currents until they touch every coastline and every agricultural system on the planet. What it has been doing recently, what it is doing right now, as of the measurements being processed by NOAA and by the Argo Float Network and by the satellite altimeters tracking sea surface height to within a centimeter, falls into the category of things that scientists describe carefully, in hedged language, with explicit acknowledgement of uncertainty, which is itself a signal. The hedging is not caution about the data is clear. The hedging is caution about what the data means, and about whether the frameworks we have been using to understand the Pacific are still adequate to describe what the Pacific is becoming. The marine heat wave that established itself in the northeastern Pacific in 2023 was not the first of its kind. The blob, as researchers informally called the anomalous warm water mass that appeared off the coast of Alaska and British Columbia in 2013 and persisted through 2015, was the first major documented marine heat wave in the region, and it produced consequences that were measured across multiple ecological and atmospheric systems. Sea surface temperatures during the blob reached 3 to 6 degrees Celsius above normal across an area of roughly 4 million square kilometers. The warm water disrupted the upwelling of cold, nutrient-rich water from depth that supports the base of the food chain. Harmful algal blooms expanded. Seabird die-offs were documented in numbers that shocked researchers who had been studying Pacific coastal ecology for decades. Salmon populations collapsed in rivers that had been productive for generations. The atmospheric ridge that sat above the warm water deflected storm systems that would otherwise have brought precipitation to California, producing one of the most severe multi-year droughts in the state's recorded history. All of this from a water temperature anomaly. All of this from a few degrees of warmth in the upper layer of the ocean, concentrated in a region that most people could not locate on a map. The blob eventually dissipated. The systems it disturbed eventually partially recovered, and then the Pacific began producing something larger. The marine heatwave conditions that developed during 2023 were structurally different from the blob in ways that oceanographers found immediately significant. The warm anomaly was not confined to the northeastern Pacific. It spread across the central and western Pacific as well, producing sea surface temperature departures from historical averages that exceeded anything in the satellite record in multiple regions simultaneously. The global average sea surface temperature in 2023 broke records repeatedly through the year, with the anomaly reaching values that the most sophisticated climate models had not projected for that specific year under any of the scenarios they had been running. This was not a projection being revised slightly upward. This was observations running ahead of projections by enough of a margin to prompt genuine discussion among oceanographers about whether the models were missing something fundamental about how heat is accumulating in and being exchanged between the ocean and the atmosphere. That discussion is ongoing. It has not produced a consensus explanation. The gap between what the models predicted and what the instruments measured is not small enough to attribute to natural variability with the kind of confidence that would allow the scientific community to move on without further investigation. El Niño and La Niña, the two phases of the El Niño Southern Oscillation, the dominant mode of interannual climate variability on Earth, are the framework through which most people understand the Pacific's behavior. El Niño brings warm surface water to the central and eastern tropical Pacific, weakening the trade winds and disrupting weather patterns across the entire globe. La Niña does the opposite, strengthening the trade winds and allowing cold water to surface in the east. The cycle plays out over roughly 2 to 7 years and has been studied intensively for decades. But what has been happening in the Pacific recently does not fit cleanly into the ENSO framework. And this is where the anomaly becomes genuinely puzzling to the specialists who study it. The warm conditions in 2023 arrived alongside an El Niño event, as might be expected. El Niño brings warm tropical Pacific surface temperatures. But the anomaly extended far beyond what El Niño alone could explain. It persisted into the La Niña transition in ways that La Niña would normally suppress. The magnitude in certain regions exceeded what the historical ENSO relationship would predict by enough that researchers began asking whether a superposition of ENSO forcing and something else was occurring, and whether that something else is a new and persistent feature of the Pacific's thermal state, rather than a temporary departure from it. The Argo Float program, which has been deploying autonomous floats throughout the global ocean since the early 2000s, provides a picture of subsurface ocean heat content with a completeness and continuity that was previously impossible. Before Argo, the ocean's interior was sampled sporadically through ship-based observations and isolated instrument deployments. Argo changed this through sheer instrument density, roughly 4,000 floats circulating through the world ocean simultaneously, each diving to a depth of 2,000 meters, measuring temperature and salinity on the way down and on the way up, surfacing to transmit data to satellites, then diving again every 10 days. The dataset this produces is one of the most important in the history of oceanography, and what it shows about the Pacific is not reassuring. Ocean heat content in the upper 2,000 meters of the Pacific has been increasing at a rate that accelerated noticeably after approximately 2014, the same period during which global average surface warming appeared to reaccelerate after the so-called hiatus of the 2000s. The heat is not just sitting at the surface where it can be measured by satellites and buoys. It is penetrating into the subsurface layers, accumulating in the intermediate waters that exchange with the surface on timescales of years to decades. This matters for several reasons, one of which is that heat stored in the subsurface ocean is heat that will be slowly released back to the surface and to the atmosphere over years and decades, even if surface forcings were to remain constant, which they are not doing. The Pacific Decadal Oscillation is a climate pattern that operates on timescales longer than ENSO. Its warm and cool phases tend to persist for roughly 20 to 30 years rather than 2 to 7. During its warm phase, the northeastern Pacific is anomalously warm, the tropics are anomalously warm, and certain regions in the central Pacific are cooler than average. During its cool phase, the pattern approximately reverses. The PDO shifted into a warm phase around 2014, which partially explains the acceleration in global surface warming and ocean heat uptake in the years since. But the PDO is itself a descriptor of a pattern rather than an explanation of a mechanism. Saying that the PDO is in its warm phase describes what the Pacific looks like without fully explaining why, and without placing a firm upper bound on how warm a PDO warm phase can get in a climate system that is itself accumulating heat through the greenhouse effect. The interaction between the PDO and anthropogenic warming is an area of active research with significant uncertainties. And what the current warm phase looks like in the context of a warming world is genuinely unprecedented in the instrumental record. There is no previous warm PDO phase against which to compare what is happening now, because no previous warm PDO phase occurred with the same background forcing from greenhouse gases. The biological consequences of persistent warm anomalies in the Pacific are not theoretical projections. They are documented observations from the ongoing reality of ecosystems responding to conditions that fall outside the range their constituent species have adapted to over thousands of years. Coral reef bleaching in the Pacific has occurred in multiple successive events since 2016, at a frequency and geographic extent that gives individual reefs insufficient time to recover before the next thermal stress event arrives. The Great Barrier Reef, the largest coral reef system on Earth and technically located in the Coral Sea rather than the open Pacific, experienced its most extensive bleaching event in recorded history in 2022, affecting more than 90% of the reef's surveyed area. The mechanism is straightforward. Corals live in symbiosis with photosynthetic algae called zooxanthellae, and when water temperatures remain a degree or two above the coral's thermal tolerance for several weeks, the corals expel the algae, turn white, and die if conditions do not return to normal quickly enough. The frequency of bleaching events has increased to the point where the thermal windows between events in many regions are too short for full recovery. The bleaching that has occurred in recent years is documented, photographed, measured, and mourned by the researchers who have spent their careers studying these systems. It is not a projection. It has already happened. Seabird populations along the Pacific coast of North America have been experiencing catastrophic breeding failures in recent years that marine ecologists link directly to the warm anomaly conditions disrupting the prey availability that seabird chicks depend on. Common murres, which raise their chicks on small schooling fish including anchovies and sand lance, experienced a die-off between 2015 and 2016 that killed an estimated 1 million birds along the Pacific coast, an event that NOAA researchers described as the largest seabird die-off ever recorded in terms of documented mortality. The warm water had pushed the cold, productive water masses where prey concentrates to depths and locations that murres could not reach efficiently enough to feed chicks. Brandt's cormorants, rhinoceros auklets, and several other species showed simultaneous breeding failures across colonies from California to Alaska. These were not gradual changes in species abundance measurable only through careful long-term monitoring. These were mass deaths, carcasses washing up on beaches in numbers that alarmed beachcombers and triggered systematic survey responses from wildlife agencies. The Pacific was warm. The fish moved. The birds died. The anomaly was not abstract for the organisms that lived inside it. Atmospheric rivers, the narrow corridors of concentrated water vapor in the atmosphere that carry enormous quantities of precipitation from the tropics toward the mid-latitudes, are directly influenced by Pacific sea surface temperature patterns. When the Pacific is anomalously warm, the moisture content of atmospheric rivers increases, amplifying both the precipitation they deliver when they make landfall and the potential for flood damage when they stall over a region. California experienced a series of powerful atmospheric river events in the winter of 2022 to 23 that broke long-standing precipitation records and produced devastating flooding and debris flows across much of the state, a whiplash from the extreme drought that had dominated the preceding several years. The connection between the warm Pacific and these events is not a simple one-to-one relationship, and attributing any specific atmospheric river to a specific sea surface temperature pattern requires careful analysis. But the general relationship between a warmer Pacific and more intense atmospheric rivers is well established in observations and in models, and the pattern of increasing atmospheric river intensity along the California coast is consistent with what would be expected as the Pacific continues to warm. The oscillation between extreme drought and extreme precipitation, the whiplash pattern, is itself a predicted consequence of warming, as a warmer atmosphere holds more water vapor and delivers it in more concentrated events when conditions for precipitation finally arrive. The jet stream's relationship with Pacific sea surface temperature anomalies is one of the mechanisms through which ocean warming translates into weather effects thousands of kilometers away from the anomaly itself. The jet stream is driven by the temperature gradient between the tropics and the poles. The larger the gradient, the stronger and more stable the jet. As the Arctic warms faster than the tropics, a process called Arctic amplification
that is occurring at roughly 4 times the global average rate, the gradient weakens and the jet becomes more meandering and more prone to forming persistent blocking patterns.
Blocking patterns are large-scale atmospheric configurations that prevent the normal eastward progression of weather systems, instead keeping a particular weather regime, hot and dry or cold and wet, locked over a region for weeks at a time. The connection between Pacific Sea surface temperature patterns and jet stream behavior is mediated through the anomaly's influence on heating and moisture of the air above them, and the connection between a warmer Pacific and more frequent blocking events is a topic of ongoing research with genuine scientific disagreement about the magnitude of the effect. What is not disputed is that blocking events have been associated with some of the most damaging extreme weather events of recent years, including the Pacific Northwest heat dome of 2021 that killed approximately 700 people in Oregon and Washington. The speed of the change in the Pacific is one of the most striking features of what is being documented, and it is a feature that climate scientists take seriously precisely because fast change is harder for ecosystems, fisheries managers, and water resource systems to adapt to than slow change. The kelp forests of the California coast are a case study in this kind of rapid change. Giant kelp requires cool, nutrient-rich water to thrive. It grows fastest in the upwelling-fed cold water of the California current system. During warm anomaly conditions, the thermocline deepens, suppressing upwelling, warming the surface water beyond kelp's tolerance, and simultaneously promoting the proliferation of sea urchins, which graze on kelp holdfasts and can rapidly convert a productive kelp forest into a barren urchin field if their populations are not controlled by their natural predators. The transition from dense kelp forest to urchin barren can happen in a matter of months, faster than management interventions can be designed and implemented. Much of the Southern California kelp forest has already undergone this transition during warm anomaly periods. Restoration efforts have been underway for years and are making local progress, but they are operating against a background of continuing thermal stress that imposes a persistent disadvantage on every restoration effort's long-term prospects. Fisheries that millions of people depend on for food and livelihood are already responding to the Pacific's changing thermal state in ways that are creating both winners and losers, with the losers tending to be communities that have less capacity to adapt. Salmon are cold water fish that depend on snow and glacial meltwater for the cool river temperatures their spawning and rearing requires, and on cold, productive ocean conditions for the years they spend at sea before returning to freshwater to spawn. Declining snowpack in the Sierra Nevada and Cascade Ranges, warmer river temperatures during summer low-flow periods, and warm anomaly conditions in the northeastern Pacific have combined to produce salmon population declines that have triggered unprecedented fishery closures. In 2023, regulators closed the entire California commercial salmon season for the first time since 2008, a closure that affected fishing communities that had organized their economies around salmon for generations. Simultaneously, certain species that prefer warmer water, Humboldt squid, various tuna species, Pacific sardines during warm phases, have expanded their ranges northward, creating different opportunities in different regions. The redistribution is not random and is not symmetric. The species moving northward are generally not substitutes for the species declining. The communities gaining are generally different from the communities losing, and the adjustment costs are falling on specific fishing-dependent communities that lack the economic diversification to absorb them. The North Pacific High, the persistent high-pressure system that sits over the subtropical northeastern Pacific and influences weather patterns along the entire western coast of North America, has been showing anomalous behavior in its position and intensity during certain recent years that researchers are beginning to connect to the broader pattern of Pacific warming. The North Pacific High normally strengthens and shifts northward in summer, blocking storm systems from reaching California and producing the characteristic dry Mediterranean climate of the California coast. Its anomalous positioning during certain recent years has contributed to both drought periods and to the atmospheric conditions that allow heat domes to develop over the interior western United States. Changes in the North Pacific high's behavior are connected to changes in the sea surface temperature gradient across the northeastern Pacific, which is itself connected to the marine heat wave conditions that have become more frequent and more persistent since 2013. Disentangling cause and effect in a coupled ocean-atmosphere system with multiple interacting modes of variability is genuinely difficult, and the researchers working on this problem are careful about drawing causal arrows. What they are less equivocal about is that the Pacific they are studying now is measurably different from the Pacific that the foundational observations underlying their statistical baselines were made on, and that baselines built on a cooler Pacific may be systematically misleading when applied to a warmer one. The Pacific's thermohaline circulation, the system of density-driven deep ocean currents that connects the surface ocean to the deep ocean and plays a fundamental role in redistributing heat and carbon globally, is not separable from what is happening at the surface. Cold, dense water formed in the high-latitude North Pacific and in the Antarctic circumpolar current sinks and flows through the deep ocean basins, eventually returning to the surface through upwelling in equatorial and subpolar regions. This overturning circulation transports vast quantities of heat, salt, oxygen, and dissolved carbon dioxide. As surface waters warm, and as freshwater input from melting ice and increased precipitation reduces the density of high-latitude surface water, the rate of deep water formation and the strength of the overturning circulation are expected to change. Whether these changes are already detectable in the Pacific in the observational record is an area of active investigation. The Pacific's overturning is generally considered less sensitive to freshwater forcing than the Atlantic's, but the Pacific is also less well observed in its deep circulation. What happens in the deep Pacific stays in the deep Pacific for centuries to millennia before emerging, which means that changes being forced now will manifest fully only long after the people currently making observations have retired. What makes this particular moment in the Pacific's history unusual is the convergence of multiple anomalies occurring simultaneously and reinforcing each other. Marine heat wave conditions are more frequent and more persistent. The background sea surface temperature is warmer. The ocean heat content is higher. The biological responses, bleaching, die-offs, range shifts, fishery collapses, are accumulating faster than they are recovering. The atmospheric responses, intensified atmospheric rivers, altered jet stream behavior, more frequent blocking, are interacting with the warmer surface in ways that amplify extreme events. And all of this is occurring on top of a long-term warming trend that is being driven by greenhouse gas accumulation in the atmosphere, a forcing that is not going to reverse on any timescale relevant to the fishermen, the coastal communities, the reef ecologists, and the water resource managers who are responding to what the Pacific is doing right now. The anomaly being described in the datasets and in the careful, hedged language of scientific publications is not a temporary departure from a stable baseline that will eventually return to normal. The baseline is moving. The anomaly is becoming the new normal. And the new normal is still changing, still warming, still accumulating heat in its subsurface layers and expressing that heat in the surface conditions and weather events that determine whether fishing communities survive, whether coral reefs persist, whether droughts last years or decades, and whether the atmospheric rivers that end those droughts arrive as rainfall or as floods. The oxygen content of the Pacific Ocean is declining in measurable ways that add another dimension to the anomaly picture. Warmer water holds less dissolved oxygen. This is basic physics, the same reason a warm glass of soda goes flat faster than a cold one. As sea surface temperatures rise and the upper ocean warms, the amount of oxygen that can dissolve into the water from the atmosphere decreases. Simultaneously, warmer surface water stratifies more strongly against the colder water below, reducing the vertical mixing that brings oxygen from the surface into the subsurface layers where marine animals live and respire. The result is an expanding oxygen minimum zone in the Pacific, a layer of water typically found at depths between 200 and 1,000 meters, where oxygen concentrations are too low for most aerobic life. The Pacific oxygen minimum zone was already among the most extensive in the global ocean before the current warming acceleration. It has been expanding both horizontally and vertically over the past several decades, as documented through repeated hydrographic surveys and through the Argo Float network. This expansion compresses the habitable depth range for fish and other oxygen-dependent organisms, concentrating them in shallower water, where they become more vulnerable to fishing pressure, surface warming, and acoustic disturbance. For deep-diving predators like tuna, the expanding oxygen minimum zone forces them to hunt closer to the surface, where they are more metabolically stressed and where their prey is also concentrated. A compression that changes predator-prey dynamics in ways that fisheries managers are only beginning to understand and model. The acidification of the Pacific is occurring simultaneously with the warming and deoxygenation, and the three stressors interact with each other in ways that compound the biological consequences beyond what any single stressor would produce alone. Carbon dioxide absorbed from the atmosphere reacts with seawater to form carbonic acid, reducing the ocean's pH. The Pacific has absorbed roughly a third of all anthropogenic CO2 emitted since industrialization, an enormous quantity that has already shifted the ocean's pH by approximately 0.1 units from pre-industrial levels, which translates to a roughly 26% increase in hydrogen ion concentration. For organisms that build calcium carbonate shells or skeletons, oysters, mussels, sea urchins, pteropods, certain corals, this acidification makes shell formation more metabolically expensive and makes existing shells more susceptible to dissolution. The Pacific Northwest oyster industry has already experienced direct economic damage from acidification. Hatcheries in Oregon and Washington began experiencing mass failures of oyster larvae around 2007 and 2008, and subsequent research traced the failures to the upwelling of corrosive, acidified water onto the continental shelf. The industry adapted by monitoring seawater chemistry and adjusting hatchery operations. But this adaptation required capital investment that smaller operations could not afford, accelerating the consolidation of the oyster industry into fewer, larger operations. Acidification did not destroy the industry. It restructured it in ways that favored those with the resources to monitor and respond, and eliminated those without them. Pteropods, tiny free-swimming sea snails, sometimes called sea butterflies, are among the most abundant animals in the Pacific and occupy a critical position in the food web as prey for salmon, herring, mackerel, and several whale species. Their shells are made of aragonite, the more soluble form of calcium carbonate, which makes them particularly sensitive to acidification. In the heavily upwelled waters of the California Current, researchers have documented pteropods with visibly dissolving shells showing pitting and erosion that was not present in historical specimens preserved in sediment cores. This is not a projected future consequence. It is a documented present-day phenomenon, photographed and measured in the organisms that are living in Pacific waters right now. A pteropod with a dissolving shell expends metabolic energy on shell maintenance that would otherwise go to reproduction and growth, reducing its fitness and its contribution to the food web. When salmon eat pteropods, they are eating organisms that are energetically compromised by the chemistry of the water they both live in. A quiet, invisible degradation of the food web that does not announce itself in the way a coral bleaching event does, but that accumulates through the ecosystem over years and decades in ways that eventually show up in salmon growth rates and survival. The Pacific's connection to the Asian monsoon is one of the most consequential and least publicly discussed links in the network of teleconnections that make the Pacific's thermal state a matter of global concern, rather than a regional one. The Asian summer monsoon, which delivers rainfall to India, Southeast Asia, and eastern China, and which is the agricultural water supply for roughly half of humanity, is driven by the temperature contrast between the warm Asian landmass and the cooler Indian Ocean and Western Pacific. When the Western Pacific is anomalously warm, it modifies the moisture flux into the monsoon, altering the timing, intensity, and spatial distribution of monsoon rainfall in ways that affect crop yields across a region that feeds billions of people. The relationship is complex and nonlinear, with different parts of the monsoon system responding differently to different Pacific temperature configurations. El Niño years are generally associated with weaker Indian monsoons and more severe droughts in parts of South Asia, a relationship strong enough that the Indian Meteorological Department includes INSO indices in its seasonal monsoon forecasts. But the relationship between long-term Pacific warming and monsoon behavior is less well characterized, and the superposition of a warming trend on top of the natural INSO variability creates conditions for which the historical relationship between Pacific temperature and monsoon behavior may not be a reliable guide to future monsoon behavior. This matters at a scale that is difficult to overstate. Failures of the Asian monsoon are not inconveniences. They are food security crises measured in hundreds of millions of affected people. The Pacific's role in modulating global carbon uptake is another dimension of the anomaly that connects ocean surface temperature to the trajectory of atmospheric CO2 concentrations. The ocean absorbs carbon dioxide from the atmosphere through two mechanisms: the solubility pump, in which CO2 dissolves into cold surface water and sinks as that water cools and becomes dense, and the biological pump, in which phytoplankton fix CO2 through photosynthesis and export it to the deep ocean as organic matter that sinks when organisms die. Both pumps are affected by warming. Warmer water is less efficient at dissolving CO2, reducing the efficiency of the solubility pump. Increased stratification reduces the nutrient supply to the surface layer, limiting phytoplankton productivity and weakening the biological pump. If the Pacific's carbon uptake efficiency decreases as the ocean warms, which is what both observations and models suggest is occurring, then more of the CO2 emitted by human activity remains in the atmosphere rather than being drawn down into the ocean, accelerating the rate at which atmospheric concentrations rise. This is a feedback loop that is difficult to quantify precisely, but whose direction is clear. A warmer Pacific absorbs less carbon, leaving more in the atmosphere, which warms the planet further, which warms the Pacific further. The magnitude of this feedback is one of the primary sources of uncertainty in projections of how rapidly atmospheric CO2 will rise under different emissions scenarios. And the current observations of reduced ocean carbon uptake efficiency in the Pacific are feeding directly into revised model parameters. The Bering Sea, at the Pacific's northern edge, is experiencing changes so rapid and so visually dramatic that researchers who have worked in the region for decades describe them in terms that go beyond scientific detachment. Sea ice in the Bering Sea forms each winter and melts each summer, and its extent and duration shape the entire ecosystem of the region, determining where and when cold, nutrient-rich water is available, providing platform habitat for ice-dependent species like walruses and ice seals, and affecting the timing of phytoplankton blooms that form the base of the food web. In the winters of 2018 and 2019, Bering Sea ice extent reached record lows, significantly below any previous minimum in the satellite record that extends back to the early 1970s. The 2018 winter was so anomalously warm that ice conditions that would have been considered extreme in any previous decade were simply not forming. The consequences cascaded through the ecosystem. Without ice-associated algae to seed the spring bloom, the timing and location of primary production shifted in ways that disrupted the feeding schedules of copepods and other zooplankton, which disrupted the feeding of young fish, which contributed to recruitment failures in commercially important species. Snow crabs in the Bering Sea experienced a catastrophic population collapse. Their biomass declined from roughly 8 billion individuals to fewer than 1 billion in a period of a few years, leading to the closure of the snow crab fishery in Alaska in 2022 for the first time in its history. The warm water that drove this collapse was not a background condition. It was an acute thermal stress event
in a population that had not experienced conditions of that severity in living memory.
The role of the Pacific in shaping North American drought cycles extends beyond California to encompass much of the western and interior United States and Canada. The megadroughts of the pre-instrumental period, droughts lasting decades or even centuries, documented through tree ring records and lake sediment cores, were associated with specific configurations of Pacific sea surface temperature that persisted for extended periods and maintained the atmospheric ridge patterns that suppress precipitation across the western continent. The tree ring record going back several centuries shows that the 20th century, during which most of the water infrastructure of the American West was designed and built, was anomalously wet compared to the preceding millennium, and that the assumed hydrology on which dam capacities, water rights, and agricultural acreages were based represents one of the wetter periods in the region's recent geological history. The drought conditions that intensified through the 2010s and into the current decade, culminating in the historically low levels of Lakes Meade and Powell that triggered the first federal water shortage declaration on the Colorado River, are better understood as a return toward more typical Western hydrology than as an anomalous departure from it, with the additional factor of warming-induced evaporation and reduced snowpack accelerating and intensifying what natural Pacific variability alone would produce. The anomaly in the Pacific does not operate in isolation from the anomaly in the Colorado River Basin or from the anomaly in the Sierra Nevada snowpack. They are the same anomaly, expressed through different physical systems. Phytoplankton in the Pacific are the foundation of everything. Every tuna, every whale, every salmon, every seabird ultimately derives its energy from these microscopic photosynthesizing organisms that drift in the sunlit surface layer. Their productivity is limited by the availability of nutrients, nitrogen, phosphorus, iron, that reach the surface layer primarily through upwelling and vertical mixing. Warm anomaly conditions suppress upwelling, reduce vertical mixing, and produce a shallower, warmer, more nutrient-depleted surface layer. Satellite observations of ocean color, a proxy for chlorophyll concentration and therefore for phytoplankton abundance, show that large regions of the subtropical Pacific have been getting less productive over the past several decades. The subtropical gyres, already the oceanic equivalents of deserts, are expanding at their edges as warming pushes the thermocline deeper and extends the zone of nutrient-depleted surface water. This is not a catastrophic collapse. Phytoplankton are still abundant in productive upwelling regions and in the subpolar Pacific where nutrients are plentiful, but a slow, sustained decline in productivity across large areas of the subtropical Pacific represents a reduction in the ocean's total biological capacity that has consequences for every trophic level above the phytoplankton, expressed over years and decades in the abundance and distribution of all the species that ultimately depend on phytoplankton carbon. The Pacific's anomaly is not playing out in a vacuum separated from the societies that border it and depend on it. The communities most directly affected by what is happening in the Pacific are often those with the least capacity to adapt. Indigenous fishing communities in Alaska, whose cultural identity and food security are inseparable from salmon and halibut. Small-scale fishing villages in the Philippines and Indonesia, whose protein supply depends on reef fish that are disappearing as reefs bleach. Coastal communities in the Pacific Islands that depend on groundwater lenses that are being contaminated by saltwater intrusion as sea levels rise above the thresholds that their geological structure can accommodate. The warming Pacific does not distribute its consequences evenly across the populations that live around it. It distributes them in ways that compound existing inequalities, falling most heavily on those who depend most directly on ocean resources, who have the least economic diversification to absorb shocks, and who have contributed least to the greenhouse gas accumulation that is driving the warming. This distributional pattern is documented in the literature on climate vulnerability and exposure, and it represents one of the most ethically significant aspects of what is occurring in the Pacific. not because the science requires an ethical frame, but because the consequences are human consequences falling on specific human communities in specific places with specific histories. The Pacific has been anomalous before. The blob was anomalous. The strong El Niño of 1997 to 98 was anomalous. Various blocking events and marine heat waves throughout the instrumental record were anomalous. What makes the current situation different is the absence of return, the absence of the reversion to mean that has historically followed Pacific anomalies and allowed ecosystems, fisheries, and weather patterns to partially recover before the next disruption. The background against which anomalies are measured is itself now anomalous. The warm conditions that would have been record-setting in the 1990s are now baseline conditions on top of which new anomalies develop. The corals that bleach during warm events are recovering more slowly because the non-bleaching intervals are warmer and shorter than they used to be. The salmon that survive the ocean heatwave years return to rivers that are warmer at the spawning grounds than the ocean years used to be. The oyster hatcheries that adapted to upwelled, acidified water are now facing water chemistry that continues to worsen past the thresholds of the adaptations they made. Everything is ratcheting. The Pacific is not oscillating around a stable mean. It is moving. The anomaly in the title of this piece is real, measurable, and documented across dozens of independent instrument networks and biological monitoring programs. And the reason it is getting bigger is that the forcing producing it, the accumulated greenhouse gases in the atmosphere, the heat banked in the ocean's subsurface layers, the loss of reflective sea ice that would otherwise bounce incoming solar radiation back to space, is itself getting bigger and will continue to do so on timescales that span multiple human generations, regardless of what emissions decisions are made in the near term. The thermal memory of the Pacific is longer than most people realize, and this longevity is one of the reasons why the anomaly described in current datasets carries implications that extend decades into the future, regardless of what happens at the surface. Water has an extraordinarily high heat capacity relative to air. It takes roughly 4,000 times more energy to raise the temperature of a cubic meter of water by 1 degree than to raise the same volume of air by the same amount. This means that the ocean does not respond quickly to surface forcing, but it also means that once heat has been absorbed into the ocean's interior, it stays there. The intermediate waters of the Pacific, between roughly 200 and 1,000 meters depth, have a typical ventilation timescale of decades. Water that entered the thermocline in the 1990s is still circulating through the Pacific's interior, carrying the thermal signature of the surface conditions during the period when it last had contact with the atmosphere. Water currently being subducted into the thermocline is carrying the thermal signature of 2023, 2024, 2025, the warmest years in recorded history, and it will release that heat slowly back to the surface over the coming decades. This committed warming, baked into the ocean's thermal structure by surface conditions that have already occurred, means that even under an extremely optimistic scenario in which surface warming were somehow immediately halted, the Pacific would continue expressing anomalous behavior for decades simply through the slow release of heat already stored in its subsurface layers. The West Pacific Warm Pool, the region of the western tropical Pacific where sea surface temperatures persistently exceed 28 degrees Celsius, and which is the largest reservoir of warm surface water on Earth, has been expanding eastward in recent decades in ways that reshape the atmospheric convection patterns that drive weather throughout the tropics and subtropics. The warm pool is the engine of the Walker circulation, the east-west overturning of the tropical atmosphere that transfers moisture from the eastern Pacific to the maritime continent of Southeast Asia and Australia. When the warm pool expands, the center of maximum atmospheric convection shifts, altering monsoon patterns, the path of tropical cyclones, and the moisture supply to rainforests in Borneo, New Guinea, and northern Australia. The expansion of the warm pool eastward is one of the documented trends in Pacific sea surface temperature over the satellite record. And it is expected to continue as greenhouse warming drives the entire tropical Pacific toward higher temperatures. But the rate at which this is occurring has accelerated in recent years, contributing to the observed changes in tropical circulation that researchers have been documenting across multiple atmospheric variables, including wind shear, cloud top temperatures, and outgoing long-wave radiation. Changes in the Walker circulation affect the frequency and intensity of drought events in Australia, the variability of the Southeast Asian monsoon, and the distribution of rainfall across the Pacific Islands, consequences that span multiple nations and multiple hundreds of millions of people. Humpback whales in the North Pacific have been exhibiting unusual migration patterns and unusual nutritional status in recent years that marine mammal researchers connect directly to the redistributed prey availability driven by the ocean's changing thermal structure. Humpbacks feed almost exclusively in high-latitude summer feeding grounds, accumulating the fat reserves they need to survive the winter migration to tropical breeding grounds where they fast. The productivity of their summer feeding grounds depends on cold, nutrient-rich water, supporting dense populations of krill and small schooling fish. During years of marine heatwave conditions, humpbacks have been documented arriving on their feeding grounds underweight, spending extended periods searching for prey concentrations, and in some cases remaining in lower latitude waters where prey is available but suboptimal, rather than completing the migration to traditional high-latitude feeding sites. Entanglement in fishing gear has increased as whales have spent more time in coastal waters where fishing effort is concentrated. A collision between the altered whale distribution and the static geography of the fishing industry that has produced elevated injury and mortality rates in several humpback populations. The whales are responding rationally to the changed conditions, going where food is, staying where conditions allow survival. But they are doing so in ways that bring them into conflict with human infrastructure that was designed around their traditional distribution, and the management systems governing both fishing and whale conservation were built around historical distribution patterns that no longer describe where the animals actually are. The Pacific's thermal anomaly interacts with tropical cyclone behavior in ways that are actively reshaping the risk landscape for the tens of millions of people who live in the path of Pacific typhoons and hurricanes. Tropical cyclones derive their energy from warm surface water. They intensify over warm water and weaken when they move over cool water or land. A Pacific with more warm surface water available over a larger area means more fuel for tropical cyclone intensification, more geographic space in which intensification can occur, and in some regions, longer seasons during which sea surface temperatures remain above the threshold required for cyclone development and maintenance. The tendency toward rapid intensification, the phenomenon in which a tropical cyclone strengthens dramatically in a short period, often jumping several categories in 24 to 48 hours, has become more frequently observed in the Pacific and Atlantic basins. Rapid intensification is particularly dangerous because it can outpace the lead time required for effective evacuation and preparation responses. A storm that is a Category 2 hurricane when evacuation orders are issued and that arrives as a Category 4 or 5 hours later overwhelms preparation systems that were calibrated for the forecast intensity. Several of the most destructive tropical cyclone landfalls in recent years have involved rapid intensification events, and the warm sea surface temperature anomalies in the Pacific and adjacent basins have been identified as a contributing factor in attribution analyses of multiple specific events. The Mindanao Current, flowing along the western edge of the Pacific in the Philippines region, and the Kuroshio Current, flowing northward along the Japanese coast, are two of the major western boundary currents that return warm tropical water toward higher latitudes and play critical roles in regional weather and marine ecosystems. Both currents have shown significant variability in recent decades, and their behavior is directly connected to the broader Pacific thermal anomaly through the wind-driven circulation changes that accompany shifts in the trade winds and the subtropical high-pressure systems. The Kuroshio Extension, the region east of Japan where the Kuroshio separates from the coast and flows eastward across the open Pacific, undergoes periodic shifts between stable and unstable states, and its stability affects heat exchange with the atmosphere over the North Pacific in ways that influence weather patterns across the western United States and Canada through downstream atmospheric effects. Research published in the past several years suggests that the frequency of transitions between Kuroshio Extension stable and unstable states has changed in the context of broader Pacific warming, with implications for the predictability of North Pacific weather on seasonal timescales. This is a relatively technical piece of physical oceanography, but its significance extends to the seasonal climate forecasts that agricultural producers and water resource managers across a large swath of North America depend on to make planting and storage decisions. The social contract around Pacific fisheries management, the set of legal frameworks, allocation systems, and scientific advisory processes that govern how Pacific fish populations are harvested, was designed around an implicit assumption of stationarity, the assumption that the statistical properties of fish populations and their environments in the future would resemble those of the past. Every stock assessment model used to set catch limits, every historical time series of biomass and recruitment that defines a stock's normal range, every reference point used to determine whether a fishery is overfished, all of it is built on data collected during a period of Pacific thermal history that is now receding into the past. When ocean conditions shift persistently outside the range of the historical data, the model's assumptions are violated, and the catch limits they produce may be systematically misleading. The most painful recent example is Alaska pollock, the most valuable fishery in the United States by volume, the fish in most fish sticks and fast food fish sandwiches. Pollock populations in certain Bering Sea management zones showed dramatic recruitment failures during the warm years, and the stock assessment models, which had been calibrated on historical recruitment relationships between temperature and survival, were not fully capturing the severity of the warm water impacts. The result was catch limits that, in retrospect, appear to have been too high for the actual state of the populations. A mismatch between the management system's assumptions and the reality of what the Pacific was doing that was only fully understood after the damage was done. The Pacific's anomaly intersects with freshwater systems across western North America in ways that compound the ocean's direct effects with changes in the snowpack, stream flow, and groundwater systems that entire regions depend on for municipal water supply, irrigation, and hydroelectric power. The Sierra Nevada snowpack is the principal freshwater reservoir for California, storing precipitation from winter storms as snow and releasing it as meltwater through spring and summer when demand for irrigation water peaks. In a warming climate, more winter precipitation falls as rain rather than snow, reducing the snowpack even in years of normal total precipitation. The snow that does accumulate melts earlier in the spring, producing peak runoff during periods when reservoir storage capacity is constrained and demand is lower, and leaving less water available for summer irrigation when demand is highest. This shift in the timing and form of precipitation, from reliable snow storage to less predictable rain runoff, has been occurring across the Sierra Nevada and Cascade Ranges for decades, and has been accelerating in the most recent period. Its connection to the Pacific thermal anomaly is through the atmospheric circulation patterns that determine when and where winter storms make landfall, their moisture content, and the temperature of the air masses they carry. A warmer Pacific changes all three of these, and the changes compound each other in ways that make the relationship between Pacific sea surface temperature and California water supply increasingly complex and increasingly difficult to manage within infrastructure designed for a different climate. Indigenous peoples around the Pacific Rim have been observing and recording changes in their marine environments for generations, and their observations frequently document shifts that predate the systematic scientific monitoring record and capture aspects of ecosystem change that instrument networks miss. Yupik and Inupiaq communities in western Alaska have described changes in the behavior, timing, and abundance of fish and marine mammals that align with and, in some cases, anticipate the scientifically documented shifts in Bering Sea conditions. Pacific Islander communities have described changes in the timing of traditional fishing seasons, in the distribution of reef species they rely on, and in the behavior of ocean currents that their navigation traditions are built around. These observations represent thousands of person-years of direct engagement with specific marine environments and carry information about ecological dynamics that would take decades to accumulate through formal scientific monitoring. The relationship between traditional ecological knowledge and scientific monitoring is improving. There are genuine collaborative programs that integrate indigenous observations with instrument data in Alaska, in the Pacific Islands, and in coastal communities throughout the Pacific Rim. But the pace of change is outrunning both the scientific monitoring systems and the traditional knowledge frameworks that have historically allowed communities to adapt to environmental variability, because both were calibrated to the range of variability that preceded the current acceleration. And what is occurring now falls outside that range in ways that leave both forms of knowledge working at their limits. The Pacific gyres, the great rotating systems of ocean current that circulate water through the subtropical ocean basins, have been accumulating plastic debris for decades in ways that are directly connected to the thermal and circulation changes driving the anomaly. The Great Pacific Garbage Patch is not a solid island of plastic. It is a diffuse accumulation of primarily microplastic particles in the convergent zone of the North Pacific Gyre, a region where surface currents concentrate buoyant debris. The boundaries of this convergent zone shift with the circulation, which is itself influenced by the thermal anomaly through the wind patterns that drive gyre circulation. Warmer sea surface temperatures and altered trade wind patterns have produced detectable shifts in gyre boundary positions that have changed the geographic distribution of plastic accumulation. Microplastics are now documented throughout the Pacific water column, not just at the surface, but at depths of thousands of meters, incorporated into the tissues of deep-sea organisms found in the sediments of the deepest Pacific trenches. They are ingested by filter feeders, by planktivores, by fish that mistake microplastic particles for prey. The chemical contaminants that adsorb onto plastic surfaces are transferred through the food chain when organisms ingest plastic-associated particles. This pollution dynamic is not caused by the thermal anomaly. It was occurring before the current acceleration. But it interacts with the thermal and chemical stresses of warming and acidification in ways that compound the burden on already stressed organisms, and the circulation changes driven by the anomaly are redistributing the plastic contamination into new regions and new depth horizons. The economic scale of what the Pacific's anomaly is disrupting is difficult to summarize in a single number, but some indication of the stakes is available through the sectors most directly dependent on Pacific conditions. Commercial fisheries in the Pacific are worth tens of billions of dollars annually at the dockside level, and considerably more when the full supply chain is included. Tourism dependent on healthy Pacific coral reefs, in Hawaii, in the Pacific Islands, in tropical Asia, represents additional tens of billions. Agriculture dependent on Pacific-influenced precipitation across Western North America and Asia runs into the hundreds of billions annually. Hydroelectric power generation dependent on Pacific-influenced snowpack in the western United States alone represents a significant fraction of the region's electrical grid capacity. Insurance losses from Pacific-enhanced tropical cyclones and atmospheric river flooding events are accelerating. None of these numbers captures the non-market values, the cultural significance of salmon to indigenous communities, the recreational and aesthetic value of healthy coral reefs, the option value of intact marine ecosystems that have not yet been pushed into alternative stable states from which recovery is extremely slow. The economic analysis, incomplete as it is, produces numbers large enough that even purely financial reasoning about the cost of addressing the drivers of Pacific warming versus the cost of continuing to absorb its consequences should produce a clear conclusion. But the economics of climate change has been producing clear conclusions for decades without those conclusions consistently translating into the policy responses they logically imply. The anomaly is real. It is documented in sea surface temperature records maintained by NOAA and by the Japan Meteorological Agency. It is documented in ocean heat content measurements from the Argo network. It is documented in the biological signals from collapsing fisheries, bleaching reefs, and dying seabirds. It is documented in the atmospheric responses from redirected jet streams, intensified atmospheric rivers, and altered monsoon behavior. It is documented in the social and economic responses from closed fisheries, revised water allocation agreements, and insurance withdrawal from coastal flood risk. All of these separate lines of evidence, collected by different agencies using different instruments measuring different quantities, converge on the same description of a Pacific Ocean that is behaviorally different from the Pacific Ocean of the mid-20th century, in ways that are large enough to matter for every human system that depends on Pacific conditions remaining within historical ranges. The anomaly is getting bigger because the forcing producing it has not stopped. The greenhouse gases in the atmosphere are still accumulating. The ocean is still absorbing heat. The feedback loops between warming and further warming are still operating. And the Pacific, the largest single feature on the surface of this planet, is still changing in ways that the instruments are still measuring, the scientists are still trying to fully understand, and the communities around its edges are living with in real time, season by season, storm by storm, catch by catch, and reef by reef. The salinity structure of the Pacific is changing in ways that amplify the thermal anomaly through feedbacks that operate over longer timescales than temperature alone. Evaporation removes fresh water from the ocean's surface, leaving the remaining water saltier and denser. Precipitation adds fresh water, reducing salinity and density. As the hydrological cycle intensifies in a warmer climate, with more evaporation in dry regions and more precipitation in wet regions, following the thermodynamic principle that a warmer atmosphere holds more water vapor and cycles it faster, the salinity contrasts between the Pacific's evaporative subtropical regions and its precipitative tropical and subpolar regions are increasing. This is documented in the Argo data as a trend towards saltier subtropical Pacific surface water and fresher tropical Pacific surface water, consistent with an amplified hydrological cycle. The significance for the anomaly is that saltier, denser subtropical surface water sinks more readily, carrying heat into the thermocline and reinforcing the subsurface heat accumulation. Fresher tropical surface water stratifies more strongly, suppressing vertical mixing and trapping warmth at the surface. These salinity-driven feedbacks are smaller in magnitude than the direct thermal forcing, but they operate in the same direction. They make the warm anomalies warmer and the cold anomalies colder, amplifying the signal rather than damping it. Climate models have historically underestimated the rate of salinity change in the global ocean relative to what observations show, suggesting that the models are also underestimating the strength of this salinity amplification feedback. Tuna are among the Pacific's most economically valuable and most ecologically significant large predators, and their response to the thermal anomaly illustrates how a commercially important species can simultaneously appear abundant and be in serious ecological trouble, a combination that creates dangerous blind spots in fisheries management. Skipjack tuna, the dominant species in the canned tuna market, are highly mobile and can move across thousands of kilometers to track their preferred water temperature range. As the Pacific warms, skipjack are shifting their distribution toward higher latitudes and into areas that were previously too cold for profitable fishing. This distributional shift has opened new fishing grounds for fleets from distant nations in the central and western Pacific, and catch volumes have remained high, which in the short term appears reassuring to fisheries managers using catch per unit effort as a proxy for abundance. But catch per unit effort can remain artificially high during a distributional shift because the fish are concentrating in a smaller geographic area where fishing pressure is also concentrating, masking the underlying abundance changes that would be visible if the fish were spread across their historical range. Several Pacific tuna species have experienced recruitment failures in certain regions during warm anomaly years, and the distributional shifts are creating allocation conflicts between fishing nations, whose exclusive economic zones are defined by geography, not by where the fish currently are, that existing international fisheries agreements were not designed to resolve. The Western and Central Pacific Fisheries Commission, which governs the world's largest tuna fishery, has been operating under scientific uncertainty about stock status that is directly related to the difficulty of assessing populations that are moving faster than the monitoring systems can track. The relationship between Pacific sea surface temperature and wildfire activity across the western United States is one of the more counterintuitive connections in the anomaly's web of consequences. Counterintuitive because fire is a land phenomenon and the Pacific is an ocean. The connection operates through precipitation. Pacific sea surface temperature patterns influence the position and intensity of the winter storm track across the western United States, determining whether a given winter delivers normal, above normal, or below normal precipitation to the interior western states. Years when the northeastern Pacific is warm and the resulting atmospheric ridge deflects storm systems northward are years of below normal precipitation across California, Nevada, Utah, Colorado, and adjacent states. Drier winters mean less snow accumulation in the mountains, less soil moisture recharge during the spring melt, and lower vegetation moisture content through the summer fire season. Vegetation moisture content is one of the most reliable predictors of fire behavior. Dry vegetation ignites more easily, burns more intensely, and spreads more rapidly than adequately moistened vegetation. The connection between specific Pacific temperature configurations and above normal fire seasons in the western United States is robust enough that researchers can use Pacific sea surface temperature data from the preceding winter to produce skillful probabilistic forecasts of fire season severity across different regions. The anomalously warm Pacific of recent years has been contributing to fire conditions through this precipitation suppression pathway simultaneously with the direct warming effect of higher air temperatures on fuel drying, two separate mechanisms operating in the same direction. Deep-sea communities in the Pacific, at depths below the sunlit zone where photosynthesis cannot occur, are connected to the surface anomaly through the sinking of organic particles from the surface layer, a process called the biological pump that delivers carbon and energy to the dark ocean floor. When surface productivity declines due to increased stratification and nutrient depletion, less organic material sinks to the deep Pacific, reducing the food supply for the deep-sea communities that depend on this particle rain. The deep Pacific is not a static, isolated realm. It is an active ecosystem with its own food webs, nutrient cycles, and biological diversity, connected to the surface by the slow rain of organic particles and by the occasional sinking of large food falls like whale carcasses. Long-term time series stations in the Pacific, including the Hawaii Ocean Time Series Station maintained by the University of Hawaii and the station Aloha maintained in the North Pacific Subtropical Gyre, have documented decadal-scale changes in particle flux reaching the deep ocean that are consistent with changes in surface productivity. These changes are small in percentage terms, but large in absolute biological impact, because the deep-sea communities they support have adapted to very low and predictable energy supplies over evolutionary timescales, and are therefore sensitive to even modest reductions in particle flux. A Pacific that is less productive at the surface is a Pacific that is also changing in its least accessible and least monitored depths. The psychology of living with an anomaly that grows larger each year is a dimension of the Pacific story that receives almost no attention in scientific literature and inadequate attention in policy discussions. The fishing families of Kodiak, Alaska, whose livelihoods depend on species whose populations are crashing. The subsistence communities in the western Pacific Islands, whose food security is eroding as reef fish disappear and as groundwater aquifers are contaminated by saltwater intrusion. The oceanographers who have spent careers studying specific Pacific systems and are watching those systems transform beyond the range of any historical analog. The water managers in California who are being asked to allocate resources from a system whose hydrology is violating the assumptions embedded in every contract and every legal framework governing water rights. Each of these groups is experiencing the same underlying physical reality through a different lens, and each is experiencing some version of the cognitive and emotional challenge of making consequential decisions in a system that is no longer behaving in the way they learned to understand it. The erosion of reliable prediction. The loss of the ability to say with reasonable confidence what next winter's snowpack will be, whether this year's salmon run will support the commercial season, whether the reef that was healthy last year will bleach this summer, is itself a form of harm that does not show up in the economic assessments, but that shapes the well-being of everyone whose life is organized around Pacific-dependent resources. The Pacific's thermal anomaly is connected to the global ocean system in ways that create feedback pathways, extending to regions apparently far removed from the Pacific itself. The Southern Ocean, encircling Antarctica, is the primary mechanism through which deep water returns to the surface after centuries of circulating through the ocean's interior. Changes in Southern Ocean dynamics, in the strength and position of the Antarctic circumpolar current, in the rate of Antarctic bottom water formation, in the melting of Antarctic ice shelves that introduces fresh water into the circumpolar ocean, affect the global ocean's overturning circulation in ways that eventually influence the Pacific. The melting of West Antarctic ice shelves in particular, accelerating under the warming ocean temperatures that are reaching the ice shelf cavities through deepened intrusions of circumpolar deep water, is adding fresh water to the Southern Ocean at rates that have increased measurably in recent decades. This fresh water reduces the density of Southern Ocean surface water, potentially slowing the sinking that drives the global overturning circulation and altering the return pathway of deep water to the Pacific surface. The timescales are long, centuries rather than decades, but the forcing is being applied now, and the committed changes to Southern Ocean dynamics that are already locked in through the warming and melting that has already occurred will be expressed in Pacific circulation and heat distribution over coming centuries, regardless of future emissions trajectories. Oceanographic research vessels are finite in number, expensive to operate, and cannot be everywhere simultaneously, which means that the Pacific's anomaly is being documented in a network that, while vastly more complete than anything available 20 years ago, still has significant gaps. The deep Pacific south of the equator and west of the international dateline is among the least monitored regions of the global ocean in terms of sustained time series observations. Sub-mesoscale processes. The small-scale ocean features with horizontal scales of 1 to 10 kilometers that play a disproportionate role in vertical mixing and in the transfer of nutrients between the thermocline and the surface are resolved by neither the Argo network nor the satellite altimetry systems that provide the broadest Pacific coverage. The autonomous surface vehicles and underwater gliders that are beginning to fill some of these gaps represent a significant advance in observational capacity, but they are deployed in relatively small numbers and concentrated in specific regions of scientific or management interest. The Pacific is vast enough that even the current observational network, impressive by historical standards, sees only a fraction of what is occurring at any given moment. This observational uncertainty compounds the uncertainty in the models, and it means that the anomaly being described in the available data is almost certainly being described incompletely, capturing the large-scale features but missing the fine-scale processes that may be important for understanding how the anomaly is evolving and where it is heading. The fishing communities of Japan, whose culture and cuisine are perhaps more deeply organized around Pacific seafood than any other national population, are experiencing the Pacific's thermal shifts as a cascade of specific disruptions to specific fisheries that together constitute a transformation of the country's relationship to its surrounding ocean. Japanese squid fishing, which has supported coastal communities along the Sea of Japan and the Pacific coast for centuries, experienced catastrophic catch declines beginning around 2017 as warm water pushed the thermal habitat of Japanese flying squid northward into waters that Japanese fishing fleets could not follow economically. Sori, a thin silver fish consumed in enormous quantities throughout Japan, the subject of autumn festivals and a fixture of the Japanese food calendar, has seen its distribution shift northward and eastward, moving away from the traditional fishing grounds close to the Japanese coast and into areas where Russian and Chinese fishing fleets have access. Japanese fishers are finding warmer water where cold water should be, absent fish where fish should be abundant, and unfamiliar species where familiar ones are not. The cumulative effect on coastal fishing communities, whose economic and cultural identity has been shaped by specific Pacific fisheries over many generations, is a kind of institutional disorientation. The accumulated knowledge of where to fish, when to fish, and what to expect is becoming progressively less reliable as the Pacific moves away from the conditions under which that knowledge was accumulated. The Pacific's anomaly ultimately raises a question that science can document but cannot answer alone. A question about what kind of ocean humanity is willing to maintain, and what kinds of ocean-dependent systems it is willing to sacrifice in the process of maintaining the energy and economic systems that are driving the warming. The Pacific has absorbed roughly a third of anthropogenic CO2 and an even larger fraction of the excess heat generated by the enhanced greenhouse effect, functioning as a vast planetary buffer that has slowed the rate of atmospheric warming at the cost of its own transformation. The ocean has been paying the price for the atmosphere's burden. The marine heat waves, the bleaching reefs, the collapsing fisheries, the shifting species distributions, the acidifying shells of pteropods and oysters. These are the receipts for a transaction in which the Pacific has been trading its own stability for the stabilization of a slightly less rapidly warming atmosphere. The anomaly is not a malfunction. It is a response, a measurable, documented, accelerating response of a physical system to the forcing being applied to it. And it will continue as long as the forcing continues, growing larger as the heat content of the ocean grows larger, expressing itself in weather, in fisheries, in coral reefs, and in the lives of the hundreds of millions of people whose food, water, and weather are shaped by what happens in the largest ocean on Earth. The North Pacific Transition Zone, the boundary region between the cold subpolar gyre and the warm subtropical gyre that runs roughly across the Pacific at 40 to 45 degrees north latitude, is one of the most biologically productive ocean boundaries on Earth and one of the most sensitive to the thermal anomaly. This transition zone is defined by sharp gradients in temperature, salinity, and chlorophyll, and it functions as a migration corridor and foraging aggregation zone for an extraordinary array of species. Loggerhead sea turtles, blue sharks, albacore tuna, black-footed albatrosses, sooty shearwaters, Pacific white-sided dolphins. The position and sharpness of the transition zone shifts seasonally and interannually in response to gyre circulation changes driven by wind patterns and sea surface temperature anomalies. During years of strong marine heatwave conditions, the transition zone has shifted northward. Its gradients have weakened, and the biological aggregation that normally makes it so productive has dispersed. The species that depend on it have had to search larger areas to find the prey concentrations they need, increasing energy expenditure at the same time that prey availability is reduced. Longline fisheries targeting albacore in the transition zone have experienced dramatic changes in catch rates and in the latitude at which catch is concentrated, with the fleet having to steam further north each year to find fish at historical catch rates. This northward creep of productive fishing grounds translates directly into increased fuel costs, longer trips, and diminishing returns for fishing operations whose economics were calibrated to the transition zone's historical position. The Pacific's influence on the global carbon budget extends beyond the direct uptake of atmospheric CO2 to include the cycling of methane, a greenhouse gas roughly 80 times more potent than CO2 on a 20-year timescale, from seafloor sediments. The Pacific seafloor hosts enormous quantities of methane hydrates, ice-like structures in which methane molecules are trapped in a crystalline water lattice, stable under the combination of high pressure and cold temperature found in deep seafloor sediments. As bottom water temperatures warm, and as the pressure conditions in intermediate depth sediments change, some of these hydrate deposits can destabilize, releasing methane into the water column. Most of this methane is oxidized by bacteria before reaching the surface, but not all of it, and the potential for increased methane flux from Pacific seafloor hydrates under continued warming is a recognized uncertainty in global methane budgets. The magnitudes involved are genuinely uncertain. The hydrate inventory is imprecisely known. The fraction that might destabilize under different warming scenarios is poorly constrained, and the bacterial oxidation capacity varies with water column oxygen content, which is itself declining. What is not uncertain is the direction. Warming bottom waters create thermodynamic pressure toward hydrate destabilization, and the bottom waters of the Pacific have been warming. The rate at which this is occurring and its significance for atmospheric methane concentrations are areas where additional observation and modeling are urgently needed. Pacific Island nations are facing a version of the anomaly that is not about statistical abstractions or long-term projections. It is about whether their countries will continue to exist as functioning societies in the coming decades. Kiribati, Tuvalu, the Marshall Islands, and several other low-lying atoll nations have maximum elevations of only a few meters above current sea level. Their freshwater supplies depend on the lenses of fresh groundwater that float above the saltwater beneath the islands, maintained by the balance between rainfall recharge and sea level. As sea level rises, and as wave-driven overwash events become more frequent with higher baseline sea levels, the saltwater intrusion into these freshwater lenses degrades the water quality for drinking and agriculture. The process is not linear. There are thresholds beyond which the lens collapses entirely and the island becomes uninhabitable. And those thresholds can be crossed by a combination of gradual sea level rise and a single large storm event that floods the lens catastrophically. Several of these nations have already begun negotiating land purchases and migration agreements with larger Pacific neighbors. Kiribati has purchased land in Fiji, and Tuvalu has entered an agreement with Australia that provides a pathway to climate-related migration for Tuvaluan citizens. These are not preparations for a distant hypothetical. They are emergency responses to a situation that is already materially affecting the habitability of these islands, already affecting freshwater availability and food security, already displacing communities from low-lying villages. The Pacific anomaly, expressed as sea level rise on these islands, is not an environmental issue. It is an existential national security issue for sovereign states that are members of the United Nations. The scientific community studying the Pacific is not complacent about the anomaly, but it is working with instruments and models that were designed for a Pacific that no longer fully exists. The baseline periods used to define anomalies, typically the 30-year averages from 1961 to 1990 or 1971 to 2000, standardized by the World Meteorological Organization, are now decades out of date as representations of current normal conditions. An anomaly calculated against a baseline period that was itself anomalously cool relative to the current climate is a statistic that understates the degree of departure from recent conditions. The WMO updated its standard baseline period to cover 1991 to 2020 for the most recent set of climate normals, which partially addresses this problem. But the new baseline still includes years during which the anomaly was already accelerating, meaning that the new normals are warmer than the climate system's long-term background state. There is no clean solution to this problem, given that the baseline is moving. Every measurement of anomaly is measured against a reference that is itself in motion. Researchers working on Pacific climate are increasingly describing this situation with language that acknowledges the inadequacy of the stationarity assumption. Language about non-stationarity, about shifting baselines, about the loss of meaningful historical analog, and the practical implications for how Pacific monitoring data should be interpreted and communicated to decision-makers are still being worked out. The coupling between the Pacific and the Arctic is one of the less discussed but potentially most consequential connections in the Anomaly's network of interactions. The Arctic is warming faster than any other region on Earth, losing sea ice at rates that are transforming the Arctic Ocean from an ice-covered system to a seasonally open water system within the lifetime of people currently alive. The loss of Arctic sea ice affects the albedo of the Arctic Ocean. Ice reflects incoming solar radiation. Dark open water absorbs it, creating a powerful local feedback that amplifies Arctic warming. This amplified Arctic warming reduces the temperature gradient between the Arctic and the mid-latitudes, weakening and destabilizing the jet stream. A destabilized jet stream meanders more widely and forms more persistent blocking patterns, which in turn affect Pacific surface temperatures by modifying the wind patterns that drive surface circulation and upwelling. The Pacific is therefore not just responding to greenhouse forcing directly, it is also responding to the downstream effects of Arctic sea ice loss, which is itself being driven by greenhouse forcing and by the heat transported poleward from the warming Pacific and Atlantic. These cross-regional teleconnections create feedback pathways that amplify regional anomalies beyond what local forcing alone would produce, and they are difficult to capture in models that treat different ocean basins as semi-independent systems. The economic value of what is being lost in the Pacific, not just the current productive capacity of fisheries and reefs, but the option value of intact systems capable of providing services for future generations, is genuinely incalculable using conventional economic frameworks. Ecosystem services valuation attempts to assign monetary values to the functions that healthy marine ecosystems perform. Provisioning services like fish production, regulating services like carbon storage and coastal protection, cultural services like recreation and spiritual significance for coastal peoples. These estimates, while imprecise, consistently produce values large enough to dwarf the costs of the policy interventions that could slow the rate of ecosystem degradation. But the economic logic that should drive investment in Pacific ecosystem protection keeps encountering the fundamental problem that the benefits are diffuse and long-term, while the costs of action are concentrated and immediate, and that the political economies of the nations most responsible for the greenhouse forcing are not well configured to appropriately discount future diffuse benefits relative to present concentrated costs. The Pacific is losing ecological capital faster than it is gaining the policy attention and resource investment required to slow that loss. And the gap between the rate of loss and the rate of response is itself a measurable quantity that has been widening for decades. Underwater noise in the Pacific has increased dramatically as shipping traffic has grown and as the geographic range of commercial shipping has expanded with the opening of Arctic routes and the growth of trans-Pacific trade. This acoustic dimension of the Pacific's transformation is rarely discussed in the context of the thermal anomaly, but it intersects with the anomaly's biological consequences in ways that matter for species already under multiple stressors. Marine mammals use sound for navigation, foraging, communication, and reproduction. Their sensory world is acoustically mediated in ways that terrestrial animals' worlds are not. A noisier Pacific is a Pacific in which whales have to call louder to be heard across the same distance, in which the acoustic cues that dolphins use to locate prey are masked by vessel noise, in which the ability of individual animals to find mates is reduced by the cacophony of the commercial shipping lanes that now cross every productive Pacific habitat. Species that are already redistributing their ranges and altering their migration timing in response to changing temperatures are doing so in an ocean that is simultaneously becoming louder, less oxygenated, more acidic, and less productive. These stressors do not queue up politely and take turns. They operate simultaneously on the same organisms, and their combined effects on physiology, behavior, and reproductive success are not simply additive. They interact, sometimes synergistically, in ways that make the challenge of predicting ecosystem responses to the full suite of Pacific changes genuinely daunting even for the most sophisticated modeling frameworks available. What the Pacific is producing right now, anomalous temperatures, redistributed species, collapsing fisheries, bleaching reefs, altered storm tracks, failing seabird colonies, acidifying shells, eroding Pacific Island nations, is the present tense expression of decades of accumulated forcing that was well understood in its physics before most of its consequences became measurable in the field. The atmospheric CO2 concentration crossed 400 parts per million for the first time in human evolutionary history in 2013. It has not been below that level since. It crossed 420 parts per million in 2023 and has continued rising. The physical connection between CO2 concentration, ocean heat uptake, and sea surface temperature is not disputed by anyone who has examined the evidence. The Pacific anomaly is what that connection looks like when it is expressed through the world's largest ocean over the timescales of decades across the biological, atmospheric, and social systems that depend on the Pacific remaining within the range of conditions that prevailed through the 10,000 years of relatively stable climate that preceded the industrial era. The anomaly is getting bigger because the forcing is still growing, and the forcing is still growing because the decisions that would be required to stop it have not been made at the scale or speed that the physics of the situation demands.